Any questions about what we did on Archimedes principle last class? Now, take your textbooks. Open your textbooks to page 270. That's the beginning of this chapter.
270?
270. 270. That's the beginning of this chapter. As I said earlier, the topics in this book is not organized in a proper learning order. And that's why I kept jumping from place to place. You see, we started off on page 270. We learned something about density, remember? And then I didn't go to the next page. I went straight forward and we went on to fluid pressure, pressure basically. And then Pascal's principle. And then we found out the fluid pressure in fluids and all that. And then fluids in motion. And then Bernoulli's principle, and then equation of continuity. We did all that, and then we did Archimedes' principle. Can anyone state what is Archimedes' principle?
Weight of objects.
Say once again. Archimedes' principle.
When object is submerged in fluid, it experiences an upward buoyant force which is equal to the weight of the fluid displaced by an object.
That's it. The weight of the object, when an object is submerged partially or fully in a fluid.
That's what I said, right?
Yeah, you're right. It doesn't have to be fully submerged. Even partially submerged is fine. It can. Yeah. So when an object is partially or fully submerged in a fluid, it experiences a buoyant force, which is always upward, and that buoyant force is equal to the weight of the fluid displaced by the object. Now, turn to page 272, and you can see on top there's a diagram, and see if you can understand what is being mentioned in the diagram. The diagram shows you that there is a container, and that container is called displacement container. It's got a spout. It's got a spout, and that's called the displacement container. So water is filled up to the spout, and then when the object is going in to the water, some water is getting displaced. That's why it's called displacement container. And the water is getting displaced, and you can see a little beaker catching up the displaced water, right? And that water that is displaced has a certain weight. That is the
weight of the object.
What is that? The little beaker has a little water in it, fluid in it. What is the weight of that fluid? It's equal to the
weight of the object. Force pushing up on the object.
Force pushing up on the object called what? Buoyant force. So basically that is the buoyant force. Now I'll show you another example. That is not enough. Here is another example. Let's say if an object weighs 100 newtons. So follow whatever I say, and then things will become very easy. All right. 100 newton, the weight of the object. So if I put it on a scale, a spring scale. If I hold the spring scale like this, the reading it will read here is 100 newtons. And this is hanging in air. When it is hanging in air, it weighs 100 newton and is clearly there. Now, the next picture shows you the same object is now in water or in a fluid or in water. That's a scale. And as soon as this object goes into water, some water is going to be pushed out, right? Some water is going to be pushed out. And if I put this on a scale, it will read something. Let's say it reads 30 newtons. What is this 30 Newton?
It's the amount displaced.
It is the weight of the water
Weight of the
displaced.
water displaced.
Is that clear? Can anyone tell me what the reading is here? 70. Exactly. Does it make sense now? It reads less now. Before it was reading 100. Now it is only reading 70 because the water is pushing upward and there's a buoyant force. How much is the buoyant force acting on this object upward? The buoyant force is 30. Whereas the weight of the object is 100. So 100 downward, 30 upward, the net force is 70, and that is what the scale reads. Does it make sense? And just for better understanding, I'm showing the same container here. With this beaker, the small beaker, put on a scale, and it reads 0 newtons. Because this object is still outside. Make sense? So there is no water that is spilt into this, and it reads 0. As soon as the object goes inside, some waters, this is the water displaced. And the displaced water has a weight, which is equal to the buoyant force. Clear? So looking at this, you can clearly understand what is Archimedes principle. This is Archimedes principle. When an object is submerged into a fluid, it experiences a buoyant force which is equal to the weight of the fluid displaced. When an object is submerged in a fluid, it experiences a buoyant force upward which is equal to the weight of the fluid displaced. That is buoyant force. And that is Archimedes principle.
I have a question.
Yes.
So, like, how does the buoyant force, like, determine how much, like, how does, like, the more a buoyant force there is, how does that change more water being displaced? Like, if you have
The volume.
If you have, like, just, like, a box and then submerge it in water, like, it doesn't, like, no matter how hard you put down the box into the water, like, wouldn't, like, the same amount of water be displaced?
Yes, true. So the buoyant force is going to stay the same wherever you put it.
Like, no matter how hard you throw the box in the water.
What do you mean hard you throw? I don't understand that.
Like, the more force. Like,
You're not applying any force from the outside. You're just like putting it in. You're just putting it in.
I'm so confused.
You're not supposed to throw the box in.
You're just supposed to let it submerge.
It's an object. It's not a box. This is an object.
Oh, okay.
It's a block of steel. Let's say. It's a block of steel.
Oh. So when you say newtons, that's just like gravity.
Yeah.
Okay.
This is a steel block. And the steel block weighs 100 newtons in air. And then when the same steel block is immersed into water or any fluid, it actually weighs less. That's because buoyant force is coming in helping it.
Okay.
And that is a buoyant force. And then for the entire chapter, you need to know basically 2 equations. So don't look at any other equation that is being thrown in this on this page. Forget about all of that. You need only 2 prime equations. Write it down. The weight of the object. What is the weight of the object? It is basically the mass of the object times gravity. Is that right? Weight of the object is mass of the object times gravity. So basically the weight of the object is volume of object times density of object times gravity. This is one equation. So I'm just writing the mass of the object as split up into volume and density. That's one equation. Any questions about that equation? No?
We did this last class.
We did? We did.
Yeah.
Yes, you gave us these equations.
Yeah, I gave you, but I'm putting it down again so that you know. Now, what is the other equation? It's a buoyant force. What is buoyant force according to Archimedes' principle?
When an
Density.
object floats the ball. Weight
Yeah,
of the fluid displaced.
It's the weight of the fluid displaced. Not weight of the object, but weight of the fluid displaced. So this one. That is buoyant force. Mass of the fluid displaced times gravity. That becomes weight of the fluid displaced. Is that clear? Okay. So do the same thing. Buoyant force is volume of fluid displaced times density of fluid displaced times gravity. There it is. The two prime equations. With those equations, you can solve any kind of problem. You don't need other equations. So do not memorize anything else other than, like, even this one does not require to be memorized. You understand Archimedes' principle, you'll be able to write those things down. So no matter how difficult the problems are on this chapter, that will help you. And we'll see how we are going to solve problems here. Any questions about this? What do you see on the board? So let's dive into problems now, straight away. And I'm going to lead you through the problem solving, and I want you to think every step and reason out why it's happening like this. You cannot solve these problems by a ready-made equation. Straightforward. You cannot solve it by a ready-made equations. You need to really think and apply. Okay? So again, Archimedes' principle simply says any object in a fluid experiences a buoyant force which is equal to the weight of the fluid displaced by the object. So I'm leaving it there. Now turn to the next page. We'll go straight into page 275 where there are problems. And we're going to solve each problem here with understanding. You're not going to there's no shortcuts for these. So you have to understand what's going on. Okay. Let's start with the first question. I'm going to read the question. Then, as you know, a drawing will be a very good way of understanding stuff. The previous drawing that I drew, was it making Archimedes' principle clearer? Was it making it clearer? The little beaker catching some water or the fluid, and the weight of that is the buoyant force. All right, now let's do the first question. The first question says, a piece of metal weighs 50 newtons in air. So I'm going to draw that straight away. It weighs 50 newtons in air. So here it is. That's a scale. And that's the object, 50 newtons in air, which is the weight. The weight of the object is 50 newtons. Let's go to the next. And 36 newtons in water. The same object weighs 36 newtons in water. So here's my drawing. So this is 50. And the same object weighs 36 newtons in water. Okay? And then it says, and 41 newtons in an unknown liquid. So here it is. Unknown liquid. This is what one line over there is all this. A piece of metal weighs 15 newtons in air, 36 newtons in water, 41 newtons in that liquid. And what's the question asking you to find? Find the density of the metal So basically they're asking you to find the density of the object, and you're supposed to find the density of this liquid. Density of the liquid. And what is this? It's a density of water, which is 1000 kilogram per meter cube. That is something that is known. Density of water is taken for granted always as 1000 kilogram per meter cube, density of water. So even if it is not given to you, just take it straight away. Unless you are given seawater or something like that, then they will give you the numbers. Okay? But if it's just water, take it 1000. So water is 1000. And this density we don't know. That's a question. So basically they're asking you to find the density of the object and the density of the fluid. Okay? Is that clear? But we can't actually go straight into it without thinking further. Now the thought process goes like this. Looking at these two pictures, can anyone tell me how much buoyant force is acting on this?
14.
14. There we go. See, I'm asking you to think. Because everything is there. You have to just pull it out. Information is there, but you've got to pull it out. What is the buoyant force here?
14.
So the buoyant force here is 14 newtons. And what's the equation for buoyant force? So let me write it down. So buoyant force is volume of fluid times density of fluid times gravity. In this case, 14 is what? Volume of what fluid?
Water.
So volume of water displaced times 1000 times, yeah, leave it as G for the time being. Is this clear?
Yes.
Okay, good. On this side, weight of object is 50. What is the equation for weight of object? So 50 is equal to volume of
Object.
times density of object, which we don't know, times
Gravity.
Now looking at these two equations, what do you know about volume of water displaced and volume of object?
It's going to be the same.
It's going to be the same.
You can't say that.
They should cancel out. But before you cancel out, now how do we actually start meddling with these two equations? This is what you do. Divide this equation with this equation, or this with this. Decide which one you want to divide. So, look what I'm doing. 50 divided by 14 equal to VO rho O G divided by VW 1000 G. Is that clear? I'm just dividing the two equations. Now what can you do here?
Cancel out.
Cancel out the G's. Then
Cancel out the V's.
cancel out the V's because they are both the same volumes.
And then divide by 50.
Now you know what to do from here on. It's straightforward. Go ahead, multiply, cross multiply. Cross multiply from there. And then you can solve it. So 50 times 1000
50,000.
is equal to 14 times rho O. So what is rho O? Solve it. Yeah, 50,000 divided by 14 in 3 sig figs. Tell me what the numbers are. I have not done anything big. I just wrote down the two equations straight away with the information that we derived, and we ended up getting two equations, and we just like dividing the two equations. 3,000 and
Will be 3571.
3571.
She said 3.
Okay. 3570 kilogram per meter cube. We solved the first part. The density of the metal, which is the density of the object, is right there. And what are they asking next? Density of the? Okay, so we'll go there then. So before you go there, look at this number. So how much is the buoyant force? Yeah. So the buoyant force here is 9 newtons. Buoyant force is 9. And now use the equation for buoyant force and set up that equation. 9 equal to volume of liquid displaced times density of liquid displaced times gravity. Just as we did earlier, we can now take this equation and divide one by the other.
Why?
Because then division is the best way to cancel off so many things. See how easily we cancel them off here?
Yeah, but like, why would you divide? Like, what's the logical reasoning behind the way?
Division. Good question. And I'll get back to that soon. Okay? I'm going to get back to him. So he's saying, why do we have to divide? I showed you. When I divided it, I see, look at this. Look at how simple it is.
Yeah, I know, but like, what's the purpose?
Okay, we'll get there. So now I'm going to use this equation and this equation, I'm going to divide it, which is a mathematical step which can be used in math. If you're actually in algebra, if you have two equations and if you're like, okay, I think division of those two equations will make things easier, then go ahead and do it that way. Sometimes that make things easier. So I'm showing the easier way of doing it. So 14 divided by 9. I'm dividing this equation with that equation. 14 divided by 9 is volume of water times 1,000 times G divided by volume of liquid times density of liquid times gravity. You know why I wrote like that. So what can he cancel? The G's and the volume of water displaced and the volume of unknown liquid displaced are exactly going to be the same. So cancel that also. Now cross multiply. Cross multiply. And then you get, there it is. Yeah, so 14 rho L is equal to 9 times 1,000. So rho of the liquid is how much?
640.
640.
643.
That's okay. 643. All right. 643 kilogram per meter cubed. We solved it. We have done. The problem is finished because the questions they're asking is like, what is the density of the metal? There it is. What's the density of the unknown liquid? There it is. Now let's go back to T's question of like, why do we have to divide? So I'm erasing this. All right, now I'm not going to divide. I'm just going to use substitution method.
Oh, never mind.
Substitution method. Okay, what's substitution method? The volume of the water displaced, how much is that? It's 14 divided by 1,000 G. Right? And since the volume of water displaced is the same as the volume of the object, I'm going to substitute that into this equation. So what happens here, it's 50 equal to 14 over 1,000 G, because I'm substituting for this, times density of the object times gravity. And the gravity cancels. Can we solve density of the object from here? And that's the same thing. So this is called substitution method, which is sometimes kind of unnecessarily complicated. Sometimes substitution method is the best way to go. But in these cases, division will be the best way to go because it's far easier to compare those things. You don't want to substitute stuff. Division makes it much easier. Okay? You get it?
How are the equations like related?
They are related. That is why division method actually works much better here. Yes.
Okay, so it's kind of.
Well, whatever works for you, mathematically, whatever works for you is acceptable.
Oh, never mind. I understand now.
Got it now? So, by substitution method, we are exactly mathematically correct. Division method, we are mathematically correct as well. Some places, division method will be much
They're
easier.
both volume times density times gravity, but it's for like different things.
Different things, yes. It's always, as I said, I've not used any other equation, only those two. Nothing more. But this is how we solve with understanding. And I'm not using blindly some equations. If you look at the solved, the examples which are solved there, or the previous page, you'll see tons of equations, like they're just throwing a lot of equations. But that's not how you solve problems. You solve problems with real understanding of Archimedes principle. That's it. Then you can just easily go ahead. And only those two equations are required if you are actually really understanding what's going on. Okay, so is this clear? Substitution method or division method, both are okay. And I'll show you another division method advantage. Suppose I have 50 is equal to xy squared times z cubed. And then 25 is equal to xy squared z squared. How much is z? 2.
Oh,
Now, division method will work much better here than substitution method. For substitution method, you will have to substitute for one into the other. Like you have got to get an expression for x from here and substitute it here.
oh.
Instead of that, if you divide it, see what happens? X gone. Y square gone. Z square and z cubed, one z is left behind there. So z is 50 over 25 and the answer is 2. See the division method? So sometimes the advantage is there. Division method gets you to the answer straightforward, like an ACT.
Oh, you saw the ICT question.
Yeah, I mean if there are two equations like this and what is z? I gave you one of the easiest ones.
You should help us with ACT for science.
I did earlier, but science is different from. Science is not the same. All right, any questions about this problem? Any questions here? Let's go to the next question. Again, reading the question, understanding it, drawing it, all this is required for proper solving. Now remember, no questions are going to look alike. It's not like in math where you actually kind of, oh, this is one example and there are tons of questions of the same type. No. Like every question is different because everything requires you to think practically, think creatively, and solve it. Right, Jake? Put that down.
Creatively solid.
Yeah, that's important to go. All right, next one says a 2.8 kilogram rectangular air mattress. You know what an air mattress is? Okay. It's a rectangular air mattress and is 2 meters long, 0.5 meters wide, and 0.100 meters thick. What mass can it support in water before sinking? So it's a practical scenario. You know what an air mattress is. So here is an air mattress. And they said the dimensions of the air mattress. 2 meters this way, 0.5 meters this way, and 0.1 meters this way, right? And what is happening? This air mattress is sitting on water now. And they're asking, what mass can it support before fully going down? So I'm going to draw the diagram for the air mattress sitting on water first. So here is the air mattress sitting on water. Not easy to draw the entire thing, but at least you can understand what's going on here. So this is 2 meters, this is 0.5 meters, and this side from here to here is 0.100 meters, the air mattress. And what is the mass of the air mattress? So 2.8 kilogram is the mass of the air mattress. Now, can you see something special here? What's this? It's partially submerged. Why should that go down? Why should this happen?
Because the weight of the
Because there's air in it.
weight of the air mattress.
It is the weight. What is the weight of the air mattress? I mean, like, my question is, what is this doing here? Why it stopped there? Why is it not fully going down?
Because it's
You
more.
said the buoyant
it's
force
less
is
dense.
more than the weight of the mattress.
Remember, I gave you the example of the soccer ball.
The buoyant force is more than the weight of the
Buoyant
mattress.
force is pushing it.
So which one is more, the buoyant force or the weight?
It's equal. It's equal.
It's equal. That is called flotation. So that is something that you should know also. What is flotation?
When an object erodes, the buoyant force will always be equal to the weight of the object.
The buoyant force will be equal to the weight of the object. These two will be equal to each other when something is floating. When anything floats, the weight of the object is downward and the buoyant force is upward, and they cancel. I mean, they both are equal. So for flotation, the condition is the buoyant force is equal to the weight of the object. That is the condition for it. Now, if you want to write this condition down in fragments, you can do this too. Buoyant force is Vf times rho f times g equal to Vo times rho o times g. That is the condition for flotation. So there are two situations that you see now. One is when something is getting submerged, where weight is independent, buoyant force independent, and then there is something called flotation, where both of them are equal to each other. Okay, so here is the air mattress floating,
Yes.
which means there must be a buoyant force acting on the air mattress, which is equal to the weight of the air mattress. But that's not the question. The question is asking, like, what mass can it support before fully going down? Like, if you take an air mattress and put it into the pool, can I just sit on it and it's fine?
Maybe.
Can another person jump on it and it's fine? How many people can it support? Maybe
Maybe two, three.
maybe 2 or 3. Can 10 people sit on it?
Yeah.
Let's find out. That's basically the question. They're asking what mass can it support. This is a realistic air mattress, so 0.5 meters. It's not that big. So 0.5 meters is only this much.
That's not realistic.
It's a little float. It's a little float. It's only 0.5 meters here, but 2 meters down that way. Like it's 2 meters. And then the height of the air mattress is this much. So that's practically what it is. Now, can we figure out how much is this? Like how much it's gone into the water? Like can we figure out this x? We can. We should be able to figure that out from the use of this equation. Let's do that first before we jump into the actual question. So let's find out how much of the air mattress must be underwater. Let's find that out. So since it is floating, the buoyant force is equal to the weight of the air mattress. So I'm going to write down all those things. What is the volume of the fluid displaced? So volume of fluid displaced times density of fluid displaced times gravity is equal to volume of the object times basically the weight. What is the volume of the fluid display? What is this green portion? How much is that green portion?
Buoyant space.
Like how much? How do you calculate it?
Um,
This is the air mattress. If it goes into, this is the water level, and if the air mattress goes this much into water, how much is the volume below? How do you find this volume?
use 1,000.
How do you find the volume of anything rectangular? Length times width times? So length times width times this height. So that's what I'm going to do. Length times width times x, this one. The whole thing is not inside, it's only this much inside. Times density of the fluid displaced, which is water, times gravity, is equal to, what is the weight of the air mattress? No, that's the mass. 2.8 times weight is mass times gravity. Right? So mass times gravity. Now, go ahead. Can you find x?
Yeah.
How much is x? This is cancelling off each other. See, look, 2 times half is 1.
2.8 divided by 1,000.
Yeah. 2.8 divided by 1,000 is 0.0028 meters, which basically means 2.8 millimeters, this much. 2.8 millimeters. That much only, it's underwater, the air mattress. So when you take an air mattress and a float and put it into water, how much has to go down? It's only that much. 2.8 millimeters is just that little tiny bit. Okay, that was not part of the question, but I'm just solving this to show you that yes, we can find out how much is submerged. Okay? And we didn't use any other strange equation. We just used the same equations and equated it. Yes?
So, do we know the mass of it right now?
We don't know. Oh, no, mass of the object is here. No, but I've not gone to the question
right,
yet.
Yeah, I know, but so can we just, so we know the actual height though, right?
Yes,
Can we just find the ratio
we
to
can.
make it equal?
We can go by ratio. But yeah, see how brainstorming comes out there? He's thinking about ratios like, okay, so if
with
this
the
much-
height, with the height and the weight.
yes,
you know?
if this much requires the air, if the air mattress weight makes it go this much, how much will make it go that much? See, he's thinking in those lines. What makes you think like that is,
Is that how you solve it or no?
no, not necessarily this way.
But if we
We
were,
can do it that way.
so would we like get like, so we would be right if we were.
You will be perfectly right.
So-
So that's what I said. If you know what's going on, and if you can use the method of proportions and get there, we can. I'll show you that method too. Okay.
Okay.
Let's do it the
Is it
usual
more-
way.
Is it more complicated the way that we're going to do it, or is it easier?
10,000 pounds.
Well, it's more understandable method. I will call it that way.
10,000.
Now, you said the proportion method, right?
Yeah.
Not everyone will understand, like, oh, the proportion method works in this case correctly. Some problems the proportion method may not work. So it may be an inverse
I'm just
proportion.
saying, yeah, I mean, with like the
It may be an
information-
inverse proportion.
with
So
the
then it will be all
information
messed up.
With the information given, you can.
Yeah. I mean, if you can correctly judge that proportion method will work fine, then that is fine. But if you make a mistake on that, it may be inverse proportion, and then you mess up the whole problem. So that's a dangerous thing to do by just assuming that proportion should work, and so let's try that. But let's try the real way of doing it. Now, this is the real way of doing it. This is water. So I'm doing it the real way of doing it. What's going on is we are putting some weights on top. So this is the air mattress. This much is inside water, right? When I put some weight on it, it goes down a bit. When I put some weight on it, it goes down further. So I keep adding weights, and when it is fully submerged, I stop. And so now the air mattress looks like this. It's fully inside water. The whole air mattress is inside, but of course there's some weight sitting on it. There are some weight sitting on it. And how much is the fluid being displaced? All that. And that is what?
100.
Exactly. So you can see the comparison here. Here only this much fluid was displaced because of this weight. But now the entire air mattress is inside water. That's because of this extra weight on top.
So
Extra weight on top.
we just plug that back into this equation.
Yeah. Evan? Okay, copy down everything. Don't miss a beat here. If you miss something here, you are not going to solve problems. guaranteed, because you won't understand what's going on. You won't be able to think in this manner. I'm just trying to lead you to why I'm recording it right now is for people to understand it at a later time, which is difficult. I'm telling you, it's difficult. This particular chapter, these kind of problems really scares many people at university level. It scares people. But if you understand what's really going on, you don't have to get scared at all. It's nothing. Yes, problems are all different from each other, but since they're all applying Archimedes principle, flotation concepts and all that, there is no reason why you should go wrong if you can just go by that method. All right, now come back here. What is happening here? The entire weight downward is balanced by all this volume. So we're going to use the same equation again. It's still kind of flotation equation. So Vf times rho f times g is the entire weight of the object. Entire weight. I'm not going to only take that. So what's the volume? 2 times 0.5 times 0.1 and times 1,000, which is for density of water, times g is equal to
100.
the entire weight, which is the entire mass times gravity. The entire mass, not just the mass of the extra stuff, the entire mass. Remember, the mattress itself is 2.8 kilograms. So all this together is this. So can we solve for the entire mass? What should be the total mass? 100. The entire mass is 100 kilograms. You can just multiply all this, and that's the answer. So if the entire mass is 100 kilograms, what should be this extra mass? 97 point? That's it. We solved it. Problem solved. And you can see clearly that you can see how much thought process went into it and how much work have we done. We did the least amount of work to get to the answer. But the understanding of the scenario is very important, right? That's why drawing properly will be a good idea to start.
How much is that in pounds? 221.
97, I'm 80 kilograms. So will it support me? Yes. I can lie down on that air mattress and still be floating.
214 pounds.
Well, it's like
Some of my mom's weight.
Yeah, you just divide by 2.2 to get it in kilograms. Whatever you are, divide by 2.2, that will give you in kilograms. I'm 80, find out yours.
24.
24 kilograms. I'm not saying your head alone, whole body. Okay. Any questions on this before we go to the next one? Okay, good. Let's go to the next one. All right. Let's go to the next question. A ferry boat, question number 3. Ferry boat is 4 meters wide, 6 meters long. Yep. They didn't tell you the height of the ferry. It's 4 meters long. I say 4 meters wide, 6 meters long. When a truck pulls onto it, the boat or the ferry boat sinks 4.00 centimeters in water. What is the weight of the truck? So now, can you imagine the whole scenario? You can imagine the ferry boat. So here is the water level. The ferry boat is already here. This is the ferry boat. And there's already kind of submerged, you know why? Because it has to carry itself, right? So it's already in. And I don't care about this. I don't care about that part. Now, what happens when the truck goes on top of it? when the truck goes on top. All right. When the truck goes on top of it, then it sinks this much. Does it look like a truck?
Yeah.
Okay.
Yeah, but there's a box ferry in there.
All right. All right. So, how much is it going down is a question. So we need this. We don't care about this part. We only need that extra. All right. Now let's read again. Ferry boat is 4 meters wide, 6 meters long, and you need to figure out now what is the weight of the truck. So the weight of the truck, weight of the truck. So why did this part sink into water? Just to balance the weight of the truck. So, oh, did I erase all that stuff? Equations? You know the equation already, right?
Yes.
Okay. So let's use the equation for flotation. Buoyant force is the weight of the truck. So if you can figure out the buoyant force, that is the answer. What is the buoyant force? Volume of fluid displaced times density of fluid displaced times gravity. And that is the weight of the truck. Volume of fluid displaced, 6 times 4 times x. Length times width times height. We don't care about the entire height. We only care about how much more it went down.
Should we assume this is fresh water?
Yes. Yeah, unless they say it is seawater, you don't have to worry. Times 9.8. That's it. Just go ahead and multiply all that, and that will be the answer. Solving it is much easier than drawing it. But drawing actually leads you to the right thought process. And what's the answer? For x. Oh, how much is x? 4. Oh, we have x.
Yeah, it's 0.0.
It's 4.00 centimeters, which is 0.04 meters. So we have to put 0.04 meters. Yeah.
Matches 960.
9,000. It's weight. We want weight. That's why I use 9.8 here. The question is not asking for the mass of the truck, it's asking for the weight of the truck. So basically you want the weight of the
truck goes away.
How much is it? 9,480 newtons is normal. Newtons. Okay, divide this with 9.8, that will tell you in kilograms. How much is that?
960.
Divide this with 9.8.
960.
No, I think 7.
Kilograms.
Yeah.
Times 2.2, that will tell you pounds.
2001.
How is it 94?
That is light.
That's very light.
You said 94.
2,000 pounds is a very light truck.
Yeah.
Yeah.
It's like a good order.
It's like- It's not even a pickup truck. A pickup truck is heavier. A pickup truck is heavier.
My car is 3,000.
Wow. It's 94.20, not 94.
All right, is that clear?
Yeah.
That's it. It's just one step, and we got the answer right there. Now the next question.
Pretty easy if you ask me. So basically, like the main thing you need to know is that the buoyant force equals the weight of
If it's floating.
what?
If it's floating.
Yeah. So if something's floating, the main thing you need to know is the buoyant force equals the weight of the
Yes.
thing that is making it.
Exactly. That's making it go down.
Yeah.
So if you step into a cruise ship, the cruise ship actually sinks by a tiny bit because it has to balance your weight. So there should be an extra buoyant force coming in because it has to balance your weight. Just like how the truck comes in and then the whole thing goes down.
Just imagine if your mom said all
All right, next question. An empty rubber balloon has a mass of 0.0120 kilograms. Empty rubber balloon. So here is an empty rubber balloon. Empty balloon. Is it 1L? Balloon is 12.
B-A-L-L-O-N.
Okay. How much is this?
0.01 or something?
0.0120. Oh, yes.
0.0120.
That's the mass of the
The
empty rubber balloon. The rubber balloon is now filled with helium at 0 degrees Celsius and 1 atmosphere pressure and a density of 0.179 kilogram per meter cubed. So the rubber balloon is now filled to a radius of 0.500 meters. And it is the fluid inside, helium, is 0.179 kilogram per meter cubed, the fluid inside. That's it. Question is, what is the magnitude of the buoyant force acting on the balloon? See figure 1.2 for the density of air. So on the previous page 271, you can see the density of air is 1.29. So density of air is 1.29 kilogram per meter cube. Now what is the question asking you? What is the magnitude of the buoyant force? So is there a buoyant force acting on this? And what's the equation for buoyant force? We already have it. What's the equation for buoyant force?
Volume.
It's volume of fluid displaced times
Rho fluid.
density of fluid displaced times gravity.
6.
So volume of fluid displaced, isn't it this volume?
Yeah.
Now what's the volume of a sphere?
2 power squared.
You're doing ACT tomorrow. 4/3 pi r cubed is the volume of a sphere. But you can also write it as pi d cubed over 6. We use that when we did the experiment. So you can use this if it is diameter, or you can use this if it's radius. But in this case, I think it will be easier to use that because what's the diameter?
1.
1. That makes easier.
One-
What is 1 cube?
1.
1.
3.1456.
Exactly. So what's the volume now? It is pi over 6. That's the volume. Times density of fluid displaced. What fluid is this displacing? Air. 1.29 times 9.8. Can you just do that and tell me what the answer is? That is the buoyant force. That is the buoyant force. Just reminding you that you have a test on this on Monday.
6.619.
So 6.62. So 6.62 newtons is acting upward because of buoyant force. Is that clear? Now what's the next question? What is the magnitude of the net force acting on the balloon? Is there any other force other than the buoyant force?
Yeah.
What is that? Other than the buoyant force, is there any other force acting on the helium balloon?
Gravity.
Okay. So there is a gravitational force, which is the weight of the whole balloon. What do you mean by weight of the whole balloon?
Volume times density.
It is weight of the balloon, the rubber itself, plus the weight of the
Gas
helium.
inside.
The helium inside. Two things. So this is the total weight.
Doesn't make them float.
Huh?
Yeah.
That's why we are trying to find the net force. So what is the total weight? What's the formula for weight? What's the weight equation? Weight of object is volume of object times density of object times.
G.
Okay, use that to find the density weight of helium. So weight of helium plus weight of rubber. Right? And weight of helium is volume of helium. What is volume of helium?
What's or that?
5 over 6. Same thing. 5 over 6 times. What's the density of the 0.179? Because what's inside the balloon is helium, so that's the density that you want. Times 9.8. Plus weight of the rubber.
0.012.
0.012 times. Okay, do that. Tell me what's the total answer. So this is the weight of the helium, and that's weight of the balloon itself. So what's the total weight? Multiply. Use your calculators.
1.036.
1.04 newtons. Okay. 1.04 newtons is the entire weight downward. What is the buoyant force though?
It's great, so it's slow.
That is why it goes up. So why is the helium balloon starting to fly upward is because this buoyant force is far bigger than this. So what's the net force?
6.62 divided by 1.4.
6.62 minus 1.
Or minus.
5.58.
It's like
yeah, that
subtract
makes
it.
sense, yeah.
5.58. So 5.58 newtons is the net force, and that is how we solve it. So did we use any other equation other than those things I wrote on the board? We use just the same equations, but in different ways. In different ways. But for everything, you need a drawing so that you exactly know what you're doing. And the only mistake that can happen over here is sometimes, the rubber, the weight of the rubber can be forgotten.
So what's the thickest
Thickest fluid, mercury.
So we could like walk on Mercury.
Okay.